We doing math today. Ain't got time for no games. We doing math today. All work and no play. We doing math today.
Good morning, guys. Let's go over lesson 4.6, the multiplication rule for independent events. We did the general multiplication rule, but this one's for specifically independent events. What are our learning targets after this lesson? You should be able to. Lesson target number 1, use the multiplication table for independent events to calculate probabilities. I'm going to show you how it's a little bit different. Learning target number 2, calculate the probability of at least one using the complement rule and the multiplication rule for independent events. And learning target number 3, determine if it is appropriate to use the multiplication rule for independent events in a given situation. So hopefully you recognize independent, independent, independent. Alright. If A and B are independent events, then the probability that A and B both occurs is the probability of A and B is equal to the probability of A times probability of B. And remember, we kind of did a play. Yeah. Let's do an example, and I think this would make sense. Suppose I will pick 2 cards from a standard deck without replacement. Okay. So a standard deck, there are 52 cards, and there are 4 shapes. So there are, this is a spade. There are 13 spades. Actually, let's see if I can do this. Magic. Bing. That's what I wanted. 13 spades, 13 clubs, and I chose it to black because they are actually called black cards. And then there are 13 red cards, 13 hearts and 13 diamonds. So that means there are 26 black and 26 are red. That's a standard deck of cards. Okay, so when it says without replacement, the first card, there are a total of 52 cards, but you pick 1 card out of the deck, and I call it the second card. You basically eat the card. You don't replace it. Your little brother was hungry. Was it probably that I select 2 spades? Now here's the question. Are these events, picking those cards, are they independent? Here's another way of saying it for independent, does the second pick, is it influenced by the first one? Well, the answer is these are not independent. Why? Because look at the numbers. You had 52 cards at first, then your little brother just ate a card, so you have 1 less card to pick from. So instead of 52 in the deck, you're picking from 51. So are these independent? The answer is no. Kind of think of it as like, you know how a lot of you guys want to move out as teenagers, and if you live in a separate apartment from your parents, what you do is what you do in your own apartment, does it change what your parents do? The answer is no. Why? Because you are independent. You do not influence them, they do not influence you. Okay, what's the probability of picking a first card, spade, and then the second card, spade? Remember, this is just the probability of a spade and spade. So we talked about that these we are going to multiply. Now, another way of saying this is, this is a review of the last lesson. The formula was the probability of A and B, and there were some conditions. The probability of A times the probability that B occurs given A. Just going to highlight that one. Just reviewing what we did last time. This is given A. B occurs given A first. So basically that means that the probability of getting a spade is given that the spade has already been drawn. So, how many cards are in the deck in the first one? There are 52. And how many spades are there? Well, there are 13 spades. And we're going to be multiplying these. But now, the influence given A, what A has already happened. You had 52 cards, now you only have 51. Okay, assume that you picked a spade in the first one. How many spades are there now? Not 13. There are -1, so there's 12. And if you multiply those, let me go ahead and multiply those and put my calculator. 13 times 12 gives me 156. And 52 times 51 gives me 2,652. You don't have to worry about a simplified fraction here. So 156 divided by 2652 gives me 0.0588, which is equivalent to about 5.88% chance that you will draw a spade on the first one, and without replacement, you will draw a second spade. Okay, let's talk about voting. Example 1b. Suppose in the area, 75% of registered voters are Republican. So let's just call this event A. In this example, everyone else is a Democrat, okay, not the independent or other political parties. So we'll call Democrat event B. And it tells us event A is first person is Republican, and then, well, this is what they want. I want event A, and I'm picking Republican, and then also in an event B, I want another Republican. Okay, so this example here, this A example, I have the probability of event A and its intersection. And remember, this is like the word what? And. So this would be probability of A times the probability of B. Well, getting a Republican is 0.75. And also getting a Republican over here is 0.75. So, if you multiply those, you'll get 56.25. There's a 56.25% chance that in this area, if I pick the first person I pick is a Republican, and then the second one I pick is also a Republican. Here's a question. Is events A and B, let's just write this out, I don't have it on there, event A and B independent? And the answer is yes. The first person does not affect the second person. That's the difference between the two examples. Okay, let's try this one over here. So I'm kind of reviewing in some ways, but also re-emphasizing some vocab that we've done before. What does this mean? The C there, remember, basically means not B. So I have the probability of A and the intersection, or times the probability of not B. What does not B mean? Well, here's event B up here, and it's saying not this. So not Republican, this would be a Democrat. And Democrat is, well, if this is 0.75, that means this has to be 1 minus 0.75, which would give you what? 0.25. So this would be the probability of not B. So you would have in some ways you can think of this, let me write it out hopefully more clearly. The probability of a Republican times the probability that the person is not a Republican, which is a Democrat. So this would be 0.75 times 0.25, and this would give you 0.1875. There is a 18.75% chance that on the first event you will get a Republican, and then the second event happening is, again, they're independent, so we can multiply them. Not a Republican, which is a Democrat. Alright, why don't you try example C and then go ahead and press pause and then go ahead and press play when you're ready. Alright, in this example, it wants the probability of, what does the C mean? So not A, and this one is the same thing, not B. Okay, A over here means event A is first person is Republican, so they don't want a Republican. What does that basically mean? Not Republican means, what's up? Other political group in this problem, that would be a Democrat. Again, this is a play on words like and, this is the intersection, so multiplication. And again, not event B, so that would be not Republican. Not Republican would be a Democrat, so we want basically a probability of 2 Democrats. And this would be 0.25 times 0.25. And I just want to review, because this is multiplication, I want to review some exponents. Super helpful for today's lesson. So when you have the same base here, and you are multiplying them, you can add the exponents. So really that's 0.25 to the power of 2. That would give you 0.0625, and if you multiply it by 100, you'll get 6.25%. There's a 6.25% chance that you get not probability A, which is a Democrat, and a probability of not event B, which is another Democrat. So Democrat and Democrat, that would be 6.25%. These are independent events. Okay, go ahead and you try example 1C, and when you're ready, go ahead and press play. No more pennies? Harris Interactive recently reported that 29% of all the US adults favored abolishing. Get rid of the penny. Suppose this percentage is true. Assuming responses from individuals are independent, so I'm going to highlight that. Responses are, too dark. Let's try that again. Are independent. Super important. What is the probability of having 3 randomly selected adults all say they favor abolishing the penny? Okay, so let's just write this out. The first person wants to abolish the penny. And then Does the first person influence the second person? The answer is no. So these events are independent, right? The first person thinks independently of the second person. It doesn't affect their outcome or probability. So this one here is also, the second person is saying abolish, get rid of it. And then the third person is also saying independently, that's why it's multiplication here. The third person is saying abolish the penny. Okay, what's the probability of abolishing a penny? Again, they're multiplication because the events are independent. Well, that would just be 0.29 here, 0.29 here, and 0.29 there. You can multiply all those, but you can just write 0.29 to the what? Third power, which would give you approximately, we should use the word approximately because you are rounding. Anytime you're rounding, you're doing the squiggly equal sign, which is called approximately 0.0244, which means there is a 2.44% chance that when you interview 3 random people in the United States, because their opinions or thoughts are independent, there's a 2.44% chance that we will find someone that those 3 will say they want to abolish the penny. So that was learning target number 1. All right, learning target number 2, we're going to focus on this concept called the at least one aspect. And you can do this 2 ways. You can use the complement rule or you can use it without, but number 1, the probability that at least one outcome happens is 1 minus the probability that no outcomes happen. A way of writing this would just be probability at least one equals 1 minus the probability that no one goes. None. 0. Let me write that in there. 0. Okay, so quite often in our house, we have 5 kids right now. Baby's coming. And my wife says, let's go to the store. Let's run an errand. And so into the van she goes. This is her. Okay. What's the probability that at least one goes? What does at least one mean? Well, it's possible that 1 kid will go. It's possible that 2 kids will go. It's possible that 3 kids will go. It is possible that four of the kids will go. Or there's a possibility that all 5 of them will go. But if she's driving like 3 hours somewhere, I don't know. There's a probability that 0 kids go. This would be the 0. This would be none. Okay? Alright. Example 2a. Defective light bulbs. A certain brand of light bulbs are defective 5% of the time. Remember, 5% is 0.05. And they are defective, which basically means they're broke. You randomly pick a package of 2 such that the bulbs off the shelf of a store. What is the probability that at least one bulb is defective? What's the keyword in this problem? At least one. Another question we should have asked is, are these events independent? The first bulb, does it affect the second bulb? Well, it's not a situation where the bulb kind of fell onto the second one. So if the first one, randomly, in the front of the warehouse, and you pick another one in the back, yes, they are independent. The bulbs don't affect one another. Okay. What's the formula used? Well, we just wrote it down. probability of at least one is equal to 1 minus the probability of none. Let's first use, let's not use the formula, and I think this will make sense. Okay, so we're picking 2 light bulbs, right? So again, we're not using the formula. I just want to show this here. And I think it'll make more sense, and then the formula will make sense. Probability of at least 1. Okay. We're trying to find those that are defective. Okay, what's the outcomes of one of these being defective? So it's possible that the first bulb we pick is defective, and then the second one is not defective. Remember, C means not. Okay. Or it's possible that the first one's not defective, but the second one is defective. Or the third one is that they are both defective, right? Because I'm trying to get at least one. One of these is a bad light bulb, right? Did you guys notice the only other outcome space that can happen in this situation is that the first one is not. I'll just write it out and cross it off. This is the other sample space. Not defective and not defective. But we don't want that. I'm trying to look for at least one defective. Okay, so again, the big idea is, because you have the word and they are independent, it's going to be multiplication. So defective is 0.5% of the time. Okay, not defective, let's just put it up here. Not defective is 0.95. Why? Because when you add up probabilities, they add up to 1. So basically, it's, how did I get 0.95? It's 1 minus 0.05. So it means you're going to get a, let's just put bad, like, this is a bad bulb, this is a good bulb. I actually like light bulbs, so yeah, it's kind of weird. 0.95. Okay, pay attention here. The word or is plus. Okay. Not defective, which means it's a good bulb, 0.95 times defective is 0.05. And then probability that they're both defective is 0.05 times 0.05. Okay, and then you can just multiply those and add them in your calculator. Let's go ahead and do that and show you. 0.05 times 0.95 plus 0.95, 0.05 plus 0.05. You must use parentheses. Alright, 0.0975. That's our answer. 0.0975. Can't write. 75. There is a 9.7% chance of finding at least one light bulb that is defective. Okay? Alright, let's now use the formula one. Same scenario. The probability of at least one is equal to 1 minus the probability of none. Okay? So I'm going to kind of put this out here. The first thing I need to do is find the probability of none. Okay, remember all that sample space we did? You have the green, the black, the blue, and the yellow, because this one over here says none of them are defective, right? So let's use that. Probability of not defective and the probability of not defective. And again, because they are independent, this is multiplication, so not defective. Means it's good. So 0.95 times 0.95. Okay, so this would give us, let's put it on our calculator, 0.95 squared. Gives me 0.0925. Okay, this is the probability of none. And then the formula has at least one. And if you just do substitution, well, what's the probability of none? That would be 0.0925. So 1 minus 0.9225, 0.0975. Which is 9.75%. Look at that, guys. Same answer. So 2 different ways of doing the same problem. You can use the formula or not, but kind of like this one only said you only had to pick 2 seats, kind of like in the van, right? And it gets a little bit more complicated when you have, like, you know, let's just say you had to pick 3 light bulbs or 5, then you would have to kind of, you know, here's at least 1 light bulb, 1 light bulb, 2 light bulbs. You have at least 1 in there, but it would be kind of a lot bigger, okay? All right, I have another example here called Winner Winner. You try it, and then when you're ready to see the solution, go ahead and press play. For a sales promotion, the manufacturer places winning symbols under the caps of 10% of all Dr. Pepper bottles. You buy a 6-pack. What's the probability that at least one is a winner? What's the keyword? At least one. And what's the formula being used? The probability of at least one is 1 minus the probability of none. Okay. You could create this huge sample space. You could get, remember these are independent events, the one bottle cap is not affecting the other bottle cap, you can have at least one winner. So let's just say you have 1 winner and 5 losers. And that's not very nice to say, but I would say not winning, okay? Or you can have 2 winners and 4 losers. Okay, so let me do a quick algebra exponent situation here. It doesn't matter where the winner is. You can have loser, 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 1, 2, 3, 4, 5, and then a winner at the very end. Or this situation. Remember, we're talking about independent events, right? So what's the probability of just getting 1? It doesn't matter the order. 2 winners. What else we got? You can win 3 times because we just need at least 1 win, and count it. You can have. I'm kind of just this algebraic notation here is just kind of making it faster instead of me writing out, you know, like what we did up here. probability to win and lose and lose and lose and lose, right? So 4 winners, 2 losers. We have also 5 winners and 1 loser. And you can actually have 6 winners and 0 losers. But the none aspect is winning none and losing all 6. Okay? So let's just, I'm doing this without the formula. So this would be probability of winning is 0.10, and losing would be 0.90 to the 5th power. Plus winning would be 10%, losing would be 90. Plus winning is 0.10 to the 3rd power, and losing would be 0.10 to the 3rd power. And then, because again, each of these have at least one W, one winner. Small mistake. Did you see it? Let's write that again. 0.90. And this one is 0.90 to the 2nd power. This one, 0.10 to the 5th, and a 0.90 to the 1st power. And a purple, 0.10 to the 6th power, and then if you know your exponents, that just means 1, which means, 0.90. It's a 0. Alright, I'm not going to do all of those on the screen. 0.10 to the 0.90 to the 5th power gives me 0.059. Let's just round to the thousandths there. This one's 0.007. You can see the probability is going down as you want more winners. The numbers are going to get really, really small. So here's the hard part if I'm doing them separately. Your calculator is going to do something like this, and that's just scientific notation. So it might just be easiest if you just do the home run by putting them all in there. And when you do, you will get 0.4686. There is a 46.86% chance that you will get at least one winner in a bottle of 6. Okay? I kind of show you that not using the at least formula is really, really a lot of work, right? So let's use the formula over here. And the probability of none, as we kind of said way over here, is 1 minus the probability that you have 0 winners and 6 losers, which would basically be 1 minus, you don't need, again, anything to the 0 power is equal to 1. That's a property of exponents. Why? That's just 1x, but you have 1 times x. Do you see that? X squared, 1 times x times x, right? You still have that idea of the 1 is still there. So losers is 0.90 to the 6th power. So 1 minus 0.96. Again, this is all 1. So 1 times anything is that number. So 0.90 to the 6th power. You will get 0.4686. Right? So you have a 46.86% chance of getting at least one winner in 6. Let's move on to, I have another example for you guys. Go ahead and try that one, and when you're ready, press play. Very superstitious. Harris Interactive recently reported that 33% of U.S. adults believe that finding and picking up a penny is good luck. So 0.33, that is good luck. Okay, just want to stop there. And what is bad luck? That would be 0.67, right? Because those probabilities add up to 1. Good plus bad equals all the outcomes of what you do for picking up that penny. Suppose the percentage is true, assuming responses from different individuals are, again, we need to have independent here in order to multiply them. What is the probability of selecting 10 U.S. adults and finding at least one who believes that finding and picking up a penny is good luck? Okay? All right. First example is finding the probability that no one is 0. What's the probability of 0? Say it's good luck. Okay? So, the probability of no one or none is the probability of how many goods. We'll call it 0 good and how many bad? 10 bad that pick it up and say it's bad. So this would be, good luck would be 0.33, and this one would be 0.67 to the 10th power. Okay? So the probability of none equals, put it on your calculator, you get 0.0182. Okay, here's a keyword. Did you notice the last one didn't have the keyword there? Just kind of helping you move along. You need at least one. So let's write down the formula. Probability of at least one is equal to 1 minus the probability of none. None is 0.0182. And if you just subtract those, then you're going to get 0.9818, which is 98.18%. That you pick 10 random US adults, and at least one of them is going to say that picking up a penny is good luck. Now, that problem would have been really bad if you did that one without the formula. But the reason, without the formula. And the reason I was trying to show you guys without the formula is to help you understand what's happening. That's all. All right, let's go ahead and try learning target number 3. All right, learning target number 3 says determine if it is appropriate or right to use a multiplication rule for independent events in a given setting. So let's review a couple of concepts here. The multiplication rule, the probability of A and B. Again, this is the intersection in your Venn diagram, right? And that is just, you might see the notation as A, this one, and B. You're going to multiply them. But this only holds if A and B are independent. but not otherwise. Okay, so what does that mean? It means if they're not independent, then you can't multiply them. Another way of saying not independent is, another way of saying independent is not independent, or we would call that dependence. So, right, most teenagers are dependent on their parents, which means they borrow your housing, electricity, food, money, your phone, your jeans. But eventually you'll become independent, which means your decision does not affect your parents, and parents' decision doesn't affect yours. Okay, if that's the case, then you can multiply them. Okay, number 2, the addition rule. Remember the word or. Is a probability of A plus the probability of B holds if A and B are mutually exclusive. Mutually exclusive. And my definition is that they mutually agree not to be part of each other's lives, which means that they can't happen at the same time. And this is my idea of yes and no, which helps you understand the concept of complementary, right? You can't say, yes, I'm going to eat this vegetable, and no, I'm not going to eat this vegetable. They can't happen at the same time. It's either a yes or no. Think back at schools, like, do I want to go to prom? Do I want to go to prom? No, I'm not going to prom. Maybe that probability is 50%, and the probability of going yes, you can't have those events yes and no happen at the same time. That's what I'm trying to make a point. Number 3, resist the temptation to use the simple rules when the conditions that justify them are not met. So just ask those questions. Are not met. Are they independent? If they are, then you can multiply them. Are they mutually exclusive? Then yes, then you can go ahead and add them. Okay? Let's try example number 3. Getting pregnant after age 55? According to the current population survey, CPS, 20% of U.S. females are older than 55. The Centers for Disease Control and Prevention, CDC, reports that 6% of all U.S. females are pregnant. Suppose that these results are accurate. If we randomly select a U.S. female is probability pregnant and probability and over 55, you get 0.06 times 0.27 equals 0.0162. Why or why not? Okay. So I see the word and. You do multiply, and if you multiply those two numbers, you will get this number. Let me prove that to you really quickly. 0.06 times 0.27. And you get 0.0162, right? So is this the case? The answer is what? We forgot to answer the question. Okay, I did it in blue, but if you look above, which one is multiplication? Is it number 1 or 2? Is it blue or red? It is blue. The question is, are these events independent? No, because one can affect the other. So the answer is no. Because being older than 55 and being pregnant are not independent events. Knowing that the chosen female is older than 55 makes it much less likely that she's pregnant. Okay, what does this mean? The reason why I said that they are not independent is because independent means that they're not related, but they are dependent because they affect one another. They influence the other one, right? If your parents lose a job, that affects you. Well, if you are age over 55, this is past general childbearing. Is it possible? I'm sure if you look it up in Google, can someone have a baby over 55? Yes, you can. Is it normal? The answer would be no. This is less and less likely. So this idea, if you're picking someone over 55, then of course less chances of being pregnant. So that one influences the other one. That's why it's not independent. They are dependent. Okay. Go ahead and press pause, and when you're ready, go ahead and press play. Let's review it all. The first trimester screen is a test given during the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. Because I'm about to have my 6th child, I kind of know what that means. Basically, they want to do a test, and the test will determine if there's something like, could your child have any disabilities? Things like that. According to the study published in the New England Journal of Medicine, approximately 5% of normal pregnancies will receive a positive result. Okay, let's just 5% you're going to be positive. Something is happening. Assume that the test results for individual women are independent. Okay, I'm just going to quickly do the math here. Well, if 5% are positive, which basically means yes, you have, there's going to be some kind of specific chromosomal abnormalities or being abnormal, not normal. What's the complement to that? 0.95, you get a negative or no. Okay, because you realize that those two numbers add up to be 1. Okay, suppose that two unrelated women who are having normal pregnancies. Okay, this is basically just telling you, well, they're telling you they're already independent. Devondra and Miranda are given the first trimester screen. Are these events independent? Does Miranda pregnancy affect Devondra's? Or does Devondra's chromosomes affect Miranda's? Well, I think they're saying unrelated because you can say, in your family history of genetics, that's what they're trying to point out. And these events are independent. Yes. D and M do not affect or influence one another. Now, if they were cousins or sisters, that would be a different issue. Okay. What is the probability that Devondra gets a positive result and Miranda gets a negative result? So let's just turn that into words. Probability that Devondra is positive and Miranda gets a negative. So that would just be the probability of Devondra getting positive, and then we're saying because the events are independent, we've already stated that. Then we can just use multiplication, and then probability that Miranda is a negative. So positive would be 0.05. And I'm looking up here, right? Negative is 0.95. And if you multiply those, you will get 0.0475. There is a 4.75% chance that Devondra will have a positive for chromosomal abnormalities, and Miranda will have a negative. Pen shut off. Whoops, that should be a C, huh? I'll change that. If 100 unrelated women with normal pregnancies are tested for the first trimester, what is the probability that at least one woman will receive a positive result? Well, I don't really want to figure out the probability of one woman. Of the 100, one gets it. The probability of out of 100, 2 of them get it, and 98 are negative. Does that make sense? That'll be too much, so we can just use the formula. Probability of at least one, that's the key word, equals 1 minus the probability of none. Okay. This would be the probability of 1 minus. Okay, none is the same word as 0. So this would be the probability of positive gets 0 times the negatives are the 100 women, right? That's saying none are positive. So this would be 1 minus, positive is 0.05 to the 0 power, times 0.95 to the 100 power. And remember, we established anything to the 0 power is equal to 1, so it's just 1 minus 0.95 to the 100th power. And when you put that into your calculator, you will get 0.00592. Remember to change a decimal into a percent. You multiply by 100. That's why I do this little 2 squiggly spots. That means there is a 0.592% chance. So this is really less than 1. Whoop. Sorry. All right, point. That's the correction. Whoops. Hey. Go there. Stay there. Okay, so 0.95 to the 100th power is 0.0592. That's my mistake. And if you subtract those, you will get 0.99408. So now if you multiply that by 100, you will get 99.4% chance that out of 100 women, at least one of those will have an abnormality in the chromosomes. Which means that's normal for people to have that. Alright, so let's review. Learning target number 1, use the multiplication rule for independent events. If we establish that they're independent, then we can multiply the 2 events. Learning target number 2, if I see the keyword at least 1, I can use the formula 1 minus the probability of none, rather than adding all of those up. And the third one, I want to make sure that I have established that they are independent, and if that's appropriate, then I can actually multiply them. And that was lesson 4.6. See you guys.